Thank you for your presence today. My name is Albert Kim, and my coworker Dr. Chitnis, and my advisor Babak Ziaie from Purdue University. Today, I'm going to present a wireless pressure sensor based on surface trap ferrofluid flow, intended to be used for biomedical applications. I'll start with the motivation, and I will discuss a little bit behind the concept and theory behind this ferrofluid-based pressure sensor, followed by fabrication and measurement. And later, I'm going to present little quick comparison with our previous design of ferrofluid sensor. And finally, I'm going to conclude the talk. The motivation of making pressure sensing device is very simple. Various bodily pressure plays an important role in medical diagnosis. For example, high intraocular pressure can cause glaucoma and eventually blindness, or high intracranial pressure can cause irreversible brain damages. And it is a long-known fact that it is important to monitor various bodily pressures. And obviously, the researcher has been working on this area over 40 to 50 years to create implantable pressure sensors, starting by pioneer work by Dr. Collin in 1967, and until recently, the capacitive pressure sensor fabricated using glass reflow technique by Dr. Weiss. However, those capacitive-based pressure sensors are based on the changing in capacitance, and it requires additional coil if we want to make it wireless. So we thought if we can make an inductive pressure sensor, we can eliminate a needs of the capacitive components. And ferrofluid pressure sensor that I'm presenting right here is answer to our question. It is inductive pressure sensor, and because there's a straight capacitance from the coil, it will be sufficient to create electrical resonance frequency, electrical resonance. And based on our thought, we presented a few different ferrofluid-based pressure sensors. So starting from the left, the very first design was a needle-based ferrofluid pressure sensor, and we presented pill-shaped ferrofluid pressure sensor. And recently, we presented acoustically powered active ferrofluid pressure sensor. However, those pressure sensor has been suffered and limited by a requirement of sufficient amount of ferrofluid requirement, and it has a relatively big form factor. Therefore, we need to design new ferrofluid-based pressure sensors. And this schematic shows our this schematic shows our pressure sensor, our new design of pressure sensor. So if you look at the left side, so this one is our new design. It consists of planar coil and small chamber that entrap in ferrofluid droplet. And as I mentioned, we need to improve our previous design in terms of ferrofluid amount usage. So we introduced hydrophilic surface in the middle, and we could entrap the ferrofluid droplet surrounded by superhydrophobic coating. And working sensing mechanism of this ferrofluid is very simple. As the pressure applies, it deflects the top membrane, and it squeezes down the droplet. And as it squeezes down the ferrofluid droplet, it covers more area of the planar coil. And of course, it allows the higher concentration of magnetic flux going through. And of course, as a response, the inductance change, and it drops the electrical resonance frequency. And this slide explains comparison between our previous design and our new design. Those two figures are our previous design. Designs are very similar, and according to external pressure, it goes to the middle or it pushes down the membrane. However, the difference between previous design and our new design is previously we transferred the ferrofluid from the reservoir and through the top of planar coil, and it has to go through the small hole and here. And our new design is only ferrofluid droplet and change only shape and increasing the area of ferrofluid that covers the planar coil. And later you're going to see, however, this is the reason that the sensitivity has been improved, and of course the dimension and geometry and material terms. The ferrofluid magnetic sensor has two parameters that are affecting to sensing mechanism. The first one is magnetic flux permeability, and the other is deflection of the polymeric membrane. And as I mentioned before, membrane deflects a ferrofluid, and of course it increases area of ferrofluid that covers on top of planar coil. And as it increases, ferrite microparticle that's suspended in the solution that allows higher concentration of magnetic flux going through the planar coil. And according to the resonant frequency of the electrical resonant frequency decrease. And as you see, this geometry only depends on the radius of ferrofluid that covers the planar coil. And this equation can be simplified based on the new terms, which depends on geometry of the device and the material constant. And with the known factor from the magnetic permeability, we need to investigate the plate bending. We take the classical theory from the plate theory, and which is a circular clamp membrane, which can be expressed based on this equation. And if deflection compared to thickness of the membrane is significantly small, then response can be expected to be linear. However, we are applying the high pressure from the various bodily pressure, which can be varies from 0 to 100 mmHg, and overall response could be expected to have nonlinear cubical response. So with the known factor from the magnetic permeability, which is a linear response, and the plate bending response, which is a cubical, overall sensing response can be expected to be cubical nonlinear response. So after go over the theory, let me discuss a little bit about simple process of fabrication. The fabrication starts with two PET films, which is one for bottom layer and the other one for top pressure membrane. This membrane is coated by superhydrophobic coating, which is commercially available. And as I mentioned, we entrap the ferrofluid in the middle by boundary of hydrophilic and superhydrophobic boundary. So for that, mechanically removable inside our middle. And then we need a little space between top and bottom layers. So we create the chamber using spacer, which fabricate using the other PET films. And then we deployed a ferrofluid droplet, and this ferrofluid droplet has been purchased commercially, which is available from banks like ProMag. And this this ferrofluid has a ferro microparticle, the mean size of 0.97 micron, and concentration of 1.33 gram per centimeter cubical. And then finally, the top membrane for pressure has been attached, and fabrication can be finished. And this is a final picture of the assembled the ferrofluid pressure sensor. The one there on the left, on your right, is completely assembled the pressure sensor, and in the middle is the bottom layer along with the ferrofluid droplet in the middle to show you the entrapping ferrofluid droplet. And this one the left picture, it is a top pressure membrane, and if you look at the top membrane, the translucent area is where the superhydrophobic coating has been applied, and mechanical removal in the middle for entrapping ferrofluid. The subset photograph right here is another angle that to show you how the ferrofluid droplet entrapping well inside of the device. And this is a summary of some of the design specifications. this top figure is indicating our new design and followed by our previous design. And as you, the dimension has been decreased a lot. We had a dimension of thickness of 1.23 millimeter, of diameter of 15 millimeter. And compared to our needle base, the very first one, it has been increased almost 90%. And compared to our second generation of Ferrofluid pressure sensor, we decreased the thickness of approximately 70%. And of course, as you indicate, the Ferrofluid we use has been decreased from 50 microliter to 5 microliter. And after we compare, and after I discuss the fabrication theory and comparison of the dimension, we need to investigate the performance of the Ferrofluid sensor using a wireless method. We use a phase steam method, and the external coil has been connected to the impedance analyzer and brought into the range of the pressure sensor. To apply the desired pressure, sensor has been inserted in small water tank that is connected to the water column, and the pressure has been applied through syringe pump that is connected to the other side of the water column. And this is the result. The plot on the right is a phase dip. It's a phase dip that's showing at the resonant frequency at given pressure. So each minima of this curve indicating resonance at the given pressure. And as you see, as the pressure increase, this curve steadily moves toward the left, which means resonant frequency drop. And the second plot is resonant frequency versus given pressure. And as we expected from our theory, response of this sensor has been showing the cubical nonlinear response. And this is a comparison between our previous design. Both one from on the right is our new sensor, and this one is from our result from our previous sensor. And as you see in the plot, both results shows nice cubical nonlinearity. However, the sensitivity has been improved from 3 kHz to 8 kHz per millimilli mercury. And this linear part, at the first linear part, we had a 12 kHz per millimilli mercury of sensitivity. So in conclusion, the Ferrofluid-based pressure sensing technique has been developed. The average sensitivity of 8 kHz per millimilli mercury, range of 0 to 60 millimilli mercury. An analytical equation has been presented for explaining nonlinear performance. And the pressure sensor has been improved compared to our previous design in terms of performance, dimension, and material. And for this work, I would like to thank all my GBMM members and NIH for funding this.